Assalamu alaikum everyone. Let us start a new chapter titled as source coding. So source coding also used for data compression. So why we need a source coding? So here is the definition. Source coding is used for data compression and is useful in storage or transmission of large volume of multimedia content, i.e. audio or video signal through a band limited channel. This is very important because all the channels are band limited, right? No channels are practically having an unlimited band. If a band is limited, then we really need to compress the data so that multimedia content, audio and videos, they can be either stored or transmitted through this band limited channel by using data compression. How this data compression happens is by the source coding. That is the definition. This is actually very important mechanism for modern digital communication or modern communication architecture. So, mm, for example, we have a source. We have a source signal X, for example. The source signal X can be expressed as a symbols of x0, x1, x2, blah blah blah. So these are the symbols. So these are the symbols in time, of course, generated by the source. Right? By the So we are already familiar with these symbols, right? All the signals we actually, because this is digital communication, we combine, we express it in number of symbols. So we are assuming we have a source signal X, which is actually can be expressed as a number of symbols generated in time. So the at any moment X signal xk, for example, signal xk at any moment. So one of the symbol xk, which is actually the which belongs to the source signal, can be expressed also as S0, S1, S2, blah blah blah, up to Sm minus 1. Here M is the number of code word. So we have a source X, and it generates symbol x0, x1, and x2 with time, of course, and the symbol belongs to a finite alphabet. So these are the source symbol belongs to a finite alphabet. So we call it a finite alphabet. Okay, they are source alphabet or source alphabet. Okay, now in this so far, whatever we have studied so far, all our communication mechanism, we have this assumption. We have this assumption of all the way, even what was our previous chapter? Our previous topics was modulation technique. Even for the modulation, demodulation, for every mechanism or scheme we discussed so far, this is our preliminary assumption. The assumption was the probability of at any time, for example k, do not depends on symbol generated previously. So what is our assumption? Our assumption is that the probability of symbols at any time, any moment, for example xk, the probability of symbols at any time k, which is termed as xk, do not depend on symbol generated previously. Okay, this is our assumption. Such kind of source, such kind of source we called discrete memoryless source. Discrete, such symbols we call discrete memoryless source. Discrete memoryless. So this is our preliminary assumptions that all symbols do not depend on the symbol generated previously. Okay, if this is the case, then we can easily write that the probability of symbol xk, the probability of symbol xk is nothing but si. Condition that x k minus 1, x k minus 2, blah blah blah, x 0. Okay, that is the condition. So easily you can write, okay, so x probability of xk equal to si, which has a fixed value. For example, give it a name pi, probability of ith. Okay, so we can write, so what is that, the probability, so we can probability of xk are fixed and do not depend on, do not depend on past symbol. In our digital modulation technique also, we generate several symbols, but the symbols do not depend on the past symbols. So they are not, symbols are generated independently, or discrete memoryless symbol. That's actually we are trying to say. So these are actually the most commonly source model. So this will be, so this will be the basis for the source model. How, when we will be creating any model or of the sources, this will be our basis of this. Okay, let's start then. What is a source coding? We know source coding is nothing but the compress data, or how to the mechanism of data compression. But what it do, it actually convert each symbol to a sequence of binary symbols. Sequence of binary symbol, or this binary symbols you can call it code word. We have used this word before, the code word, a combination of some binary symbols that represents the, or binary sequence represents as of a symbol is called code word. So in source coding, our aim is to minimize the average number of bits needed for this symbol creation. Number of bits needed to represent each symbol. For an efficient mechanism, if we want to make our source coding efficient, then we really need to know what is the efficient way to generate this code word which has a lowest or minimum bit length to represent each symbol. Okay. Okay, so the mapping from mapping from symbol to code word is termed as the code, as the code. So if we want to have a sequence of binary symbols which will corresponds to a symbol, then we need a mapping, right? For in the mapping, there will be each for each symbols there will be code word. For each symbol there will be individual code word. This mapping is called code. So from there the name came, the source coding. Okay. Okay, let's see some example. Then things will be easier. So for example, in an example, consider a simple code for an alphabet m equal to 4. Okay, consider a simple code. Simple code means this mapping. Simple code for alphabet m equal to 4 symbols. So these symbols you can term as a S0, S1, S2, S3, S3. Okay. For example, S0 will be termed as 1 1. So these are the code. So S0 is a code here. So S1 will be representing 1 0, S2 0 1, S3 at the 0 0. We have 4 symbols: S0, S1, S2, and S3, and each one is corresponding by a 2-bit symbols or bit sequence. Okay. So each code is represented by 2 bits of code length. Here you see the code length are fixed. So it's a fixed length code word. So we also observe that the codes can be mapped to the alphabet 1 to 1. Means S0 is directly mapped to 1 1, S1 is directly mapped to 1 0, 0 1, and as well as 0 0. So in recoding, eh, in the receptions, we can actually remapping immediately 1 0 to S0, 1 0 to S1, 0 1 to S2. Directly they are 1 to 1. So what is the benefit of this kind of fixed length code or direct mapping? Is actually they have a low complexity. Low complexity. And of course easy in decoding. So you are for example, this way you are encoding a 0 to 1 1. In the reverse way, 1 1 will be decoded as 0. Okay. So for example, if I take an example, this is a series of bits. This is a fixed length bit. So we know if we want to had to source code this bit stream using this code word, we know this is a 2 bit length code word. So 2 2 2. So 1 0 will be decoded as S1, 0 1 will be decoded as S2, 0 0 will be decoded as S3. So what we are saying, they are uniquely decoded, uniquely decoded, because it's fixed length. So fixed length, they have a unique means no other value will be decoded as 1, no other value will be decoded as 2 until by these their corresponding values. Only 1 0 will be decoded as 1, only 0 1 will be decoded as 2, only 0 0 will be decoded as S3. They are uniquely decoded. Okay, they are fixed length. They may not be fixed length. Okay, they may be variable length. For example, if they are a variable length code, like a variable length code, what will happen for the same m equal to 4 value? Okay, what will happen? For example, as 0 as 0, as 1 as 1, as 2 as 0 0, as 3 as 1 1. You see here we have 1 bit, here we have also 1 bit, but we have 2 bit, means they are not a fixed length code word. They are also 2 bit. That's why it's called variable length code. Now, when we'll be decoding this one, see. So, for example, you received a stream 000 bit string. How will be decoded this one? So, this can be decoded as S0 and 00. This can be decoded as S2, like S2, or it can be decoded as S0, again S0 or S0, right? Isn't it? Or what can be done, that this can be decoded as 2, this can be decoded as 0. You see, because we change the same sequence of like 000, the same sequence 000 will be corresponds to what? It can be either S0 S2, or S2 S0, or S0 S0 S0. You see, it is confusing us. Means this is not an efficient way of source coding of something. So what we can say, this is previously we say it was uniquely decoded. Means everyone has a unique representation. Every symbol has a unique code word. But here every symbols do not have a unique code word. Means actually not not uniquely decoded. Uniquely decoded. So what we can say, that what is the means actually in by this example we understand one thing, that source code should be uniquely decoded. That should be a principle. If they are not uniquely decoded, you will make wrong reception, wrong decoding of the message. So uniquely decoded, that must be a criteria for source coding, which implies that code is, for example, uniquely decoded, uniquely decoded if the original source sequence can be reconstructed perfectly from the coded sequence. So which is possible in our cases, previous cases, in uniquely decoded system. But in this example, the original source sequence cannot be actually reconstructed perfectly from the code sequence because it's confusing us, right? So this is one of the criteria for the source coding. Okay. So how to question here? You see, in our previous system, we could have uniquely reconstruct or like uniquely decoded the symbols by using a fixed length. Whenever we switch to the variable length, these condition broke down, and it's no more the uniquely decoded, right? But is it possible that uh, source code will be not fixed word but still uniquely decoded? What I'm saying is, you see here, the condition uniquely decoded arises because of this fixed length, because of this fixed length code. As soon as we switch to the variable length code, this uniquely decoded condition do not sustain. So is it possible that some code will be not fixed length as well as uniquely decodable codes? Let's see. So uniquely decodable codes. For example, S0 is represented by 1, S2 by 0, 1, S3, 0, 0, 1, and S0. Oh, this is 1, 2, 3, 0, 0, 0. What is happening here? We are having a variable code length. Let's see this variable code length becomes uniquely decodable or not. So whenever we represent in this way, we can notice that we notice then one thing. One thing is no code word is a prefix of another code word. This is actually a key to uh, not fixed length or variable length code word to make it uniquely decodable. Which the condition is no code word is a prefix to another code word. For example, 1. This 1 is not prefix to anyone. You see anyone have 1? No. At the beginning? No. So 0, 1. In any other code have in the beginning 0, 1, 0, 1? No. So it's not prefix to. This one code is not prefix to another code. Okay. So if I have a 1, 0, 0, 1, immediately 1 is a 0 and 0, 0, 1 is S2. So 0, 0, 0 is S2. So we can see no other symbol sequence corresponds to the bit sequence. They are unique. This becomes so now, though it's a variable length, it can become a uniquely decodable codes. Actually, you see, we could have remain on the fixed length, but we switch to the variable length because for the sake of efficiency. If we remains in the fixed length, we lose the efficiency. Okay, that's how we depend on the variable, but we see the variable length uh, have this tendency of ununiqueness. By choosing proper like code symbol or code word, we can make them uniquely decoding or different to each other. For example, this will be, for example, for all this example, m equal to 4, this is also m equal to 4. Just an example. Okay. So for m equal to 4, let's see. For example, S0 is 0. How not properly choosing the code word will jeopardize your process. You will see it. So S0 not equal to, it corresponds to so S0 corresponds to 0, S1 corresponds to 1, S2 corresponds to 0 0, and S3 corresponds to 1 1. What was our condition for unique decodable codes? No code word is a prefix to another code word. No code word is prefix to another code word. Okay, this for this no code word is prefix to another one. Of course, for this no code word is prefix. No, this do not follow this condition. You see, this one prefix is the same as this code word. Means actually here we make the blunder. So S0 is actually prefix in S2. So that condition do not fulfilled. So we can say that prefix free code actually is uniquely decodable. From this example and from the previous example, we can conclude that prefix free code is uniquely decodable. If you maintain the single rule, then all the equivalent code will be decodable, or they are uniquely decodable. So this is also called a instantaneous code. Instantaneous code. Why instantaneous code? Because you can instantly, you do not have to wait for the next code word or this data sequence, the bit sequence. So instantaneous code word, it means that each code word code code word is decode by itself, by means not necessary to wait for the next code word, not necessary to wait, is necessary to wait for the next code word. For example, to our previous example, this is using this example, we are writing that okay, this is stream of information is coming, bit stream 0 0 0 0 0 1 1. You see, when this stream of data comes, whatever the duration, as soon as it comes, you can say I can easily instantly decode this to S3. I can instantly decode it to S2. I can instantly decode it to S0. I do not have to wait for, for decoding S2, I do not have to wait for S0. For decoding S3, I do not have to wait for S2. Right? So, no need, or no need to wait for next code word. Next code word. That's actually we're trying to say. So prefix free code are uniquely decodable and they are instantaneously coded. Okay, so this is a criteria. Okay, so to fulfill those criteria, we had to know one thing. What is the average code length? Code length could be any size, right? This S3, S2 or S0, whatever, it can be expressed by 1, 2, 3, 4, 5, whatever, any length of uh, code code word or bit length. But what is the average code word, so that the system is very efficient? Means actually it's directly related with the compression efficiency. Compression efficiency. Compression is directly related to the compression. So let a symbol, for example SI, as a LI bit or bits actually. For example, SI have, for example, SI, sorry, SI had 000, which is actually like 3 bit, right? 3 bit, which is actually the LI, our LI, which is actually LI. So the average length of the code word can be, so average length of the code L can be expressed as all the code word from I to 0 to m minus 1 Li multiplied by to this weighted average probability of I. So it will give us the average length of the code word. So here we know, we already discussed it. What is the pi? Pi is the probability of the occurrence. Pi is the probability of the occurrence. Means actually the probability that x, our which is our signal, which is actually have Si, is the pi. We have written it previously, so we can easily find the average code length. So this is actually the our average code length. This is very important. You do not want your code length will be very long, because you lose the efficiency. Okay, so the reason you are compressing the symbols will be jeopardized if you have a very long code word. So you need actually what? You need actually optimum value. Actually we need minimize average length. You need a minimum, you need a minimum, you need minimum minimum, so you need minimum code length. So that's actually the key. By how many code word you express your symbols, the minimize the minimum the number, the efficient your code word is. Okay, so that will be actually key to this chapter, how to find a minimum length of code which will be efficient for our operation, how to find those variable conditions. Okay, thank you. Here we will ends up our recording. Assalamu alaikum.